Hi everybody, welcome to my presentation. Although we all have participated in many online presentations in the past 7 months, I still don't feel particularly comfortable recording this presentation for the conference instead of giving it in person. I especially regret that there will be no discussion after the presentation. So if you have any questions or comments, feel free to write me an email to the address that you see on the left. This presentation will present a hierarchical Bayesian approach for Gaussian random fields with conjugate priors. We will apply it to an example where we determine spatial characteristic values of material properties. From now on, I will restrict to my voice. You will not see my face anymore. The background of the model that I'm going to present stems from the structural verification of existing structures, which is often based on measurement data. With this data, you can build a probabilistic model and then use this model to determine characteristic values, which are typically quantile values of the probability distribution, for the verification of the structure. However, the existing concepts typically do not account for the measurement locations, which means that this additional information is lost and the potential correlation of the measurements is neglected. We want to use this information by using Bayesian methods. Bayesian methods can be used to combine potential prior information with the data at hand. Since they are quite flexible, they can be adapted to the problem that you're facing. Plus, you can include random field models in the update, and in special cases, when you use conjugate priors, closed form updating rules can be derived for the Bayesian update. Let's take a look at the example of a ship block chamber wall where we have various arrangement of measurement locations. The first case, we have 3 core samples in the chamber wall, and each core sample provides a number of measurements. These measurements could be, for example, the concrete compressive strength. The second arrangement is when we have evenly distributed the measurement points all over the ship block chamber wall. And in the third case, we have a local clustering of all data points. Now obviously, in the last case, the information that we get is not as global as the information that we get in the second case. However, given the approaches that are typically used, the calculated characteristic value of the material property would not differ in any of the cases, because these approaches do not account for spatial correlation of the measurement points. The idea is to model the material property as a random field x of z. In that case, the spatial correlation can be modeled explicitly and accounted for in further analysis. If one draws samples of x of z, these samples show spatial variability. I'm going to illustrate this by 2 independent samples, A and B, of the ship block chamber wall that was modeled with 2 random fields. Obviously, these realizations of the 2 random fields show the spatial variability of the material property. Then we want to use Bayesian analysis to update this random field model by combining potential prior knowledge about the material property and the data that we draw from the structure. We want to include spatial information, so the measurement locations where we get the data, in the Bayesian update. Then we can calculate local characteristic values for further analysis. On the right-hand side, you see the hierarchical Bayesian approach that we want to use to obtain these local characteristic value. I'm going to give an overview over this approach first and explain the steps more detailed afterwards. So the first step is the prior model, which is a homogeneous Gaussian random field x of z and the normal gamma distribution for the random field parameters. Second, we have a likelihood, which is a multivariate Gaussian, accounting for the spatial correlation of the measurements. Third, we have a posterior distribution of the random field parameters, which is again a normal gamma distribution due to the conjugacy of the normal gamma prior and the Gaussian likelihood. And fourth, we get a posterior predictive random field, which is a student's team marginal distribution. Now the advantage of this approach is that we can derive closed form equations for the posterior predictive random field parameters based on the prior model and the likelihood. Now a bit more detailed. The prior model is a homogeneous Gaussian random field x of z, which means that x is Gaussian at any location of the random field. The autocorrelation function ρ defines the correlation of x of z1 and x of z2 for any z1, z2 in the domain of the random field. Since x of z is Gaussian, the random field is fully defined by the mean mu, the precision lambda, which is the inverse of the variance, and the autocorrelation function. Mu and lambda are modeled as random variables, where we have a normal distribution for mu conditional on lambda and a gamma distribution on lambda. At the bottom you see the PDF of the normal gamma distribution. Now to the likelihood function. The likelihood is proportional to the probability of the data m given a state of the parameters mu and lambda. It includes information from m, so the measurement values, the measurement locations, and a potential measurement error. In our case, it's an n-variate Gaussian, where n is the number of the measurement points. The spatial correlation of the measurement locations only enters the correlation matrix Rm. Based on the prior distribution and the likelihood, we can find the posterior distribution of the random field parameters. In our case, since the normal gamma distribution is a conjugate prior for the Gaussian likelihood, the posterior distribution is again a normal gamma distribution. In that case, the Bayesian update reduces to a parameter update of the normal gamma distribution. Analytical equations can be found for the parameters alpha n, beta n, mu n, and kappa n. I'm going to show you the equation now only for mu n. It looks like this. So the information from the measurement locations and the prior parameters and the measured values enter the update. The posterior distribution is a global distribution, but we want to have a location-specific posterior predictive distribution of the random field. To this end, we have to marginalize the following integral, where the posterior distribution of the parameters f of mu and lambda given m and the location-specific random field distribution given a state of the parameters mu and lambda enter. By marginalizing over the parameter space, we get the posterior predictive distribution of x of z. And this distribution is a student's t-distribution, which is the following form. The characteristic value of the posterior predictive distribution can then be evaluated as the 5% quantile of the posterior predictive distribution of the random field. Enough of the theory, let's go to an example. I've mentioned the ship lock chamber wall several times. On the right hand side, you now see the ship lock, where we focus on one chamber wall. It's the chamber wall on the right hand side. And we want to model or analyze the spatial characteristic concrete compressive strength. Let's assume we have 3 vertical core samples in the quarter points of the ship lock chamber wall. From these core samples, we get 9 measurements from the modern concrete in the top layer and 24 measurements from the old historic tamped concrete in the bottom layer. We want to use a non-informative prior distribution for mu and lambda by choosing the normal gamma prior distribution parameters. Kappa 0 is 0, alpha 0 is minus 0.5, and beta 0 is 0. The parameter mu 0 does not have to be chosen, since by choosing kappa 0 is equal to 0, the Gaussian distribution becomes the uniform distribution on the real axis. The spatial correlation of the concrete compressive strength is modeled with the exponential model. So it's exp of minus 2 times the distance of z1 and z2 divided by 5 meters. We are assuming a log normal prior random field, so we have to do a log transformation of the data to be able to update the underlying Gaussian random field, since the updating rules are only valid for Gaussian random fields. We can then evaluate the characteristic concrete compressive strength as the 5% quantile value of the posterior predictive distribution. We can see the effects of the measurement locations, and especially regions of high and low quality concrete can be made visible. The local extrema are always at the measurement locations. And with increasing distance from the measurement locations, the effect of the measurement values decreases. However, there's also a global effect of the Bayesian updating on the characteristic values, which is due to the global updating of the normal gamma distribution with the measurement data. Now comparing the obtained values with the standardized approach of Annex D in Eurocode 0, we can see that far away from the measurements, the obtained values are significantly smaller than the ones obtained with the Eurocode. Comparing 29.4 megapascal at point A in the top layer to 39.6 megapascal from the Eurocode, and in the old tamped concrete layer, it's 6.4 megapascal far away from any measurement location, compared to 8.2 megapascal from the Eurocode. If you move closer to the measurement location, then depending on what the measurement outcome is at this location, the values can be smaller or higher, because there is the spatial correlation of the measurement location. In fact, the Eurocode approach is a special case of the presented methodology when you neglect the spatial correlation. But it can only give a single characteristic value for the given data, which then is valid for the whole structure. Let me share my conclusions with you. The presented approach provides location-specific characteristic values of the model material property. And as you have seen in the previous example, critical regions can be made directly visible. Plus, locally clustered data cannot dominate the global results, as these data points would strongly be correlated and thus have a smaller effect on points that are far away from these clusters. So overall, you get a more realistic image of the structural condition, especially considering large structures. That's all I wanted to tell you today. Thanks for watching my presentation. I really appreciate it. And once again, if you have any questions or comments, just write me an email. I will reply as soon as possible. Stay healthy, and I hope to see you all soon in person. Bye!